some of the tools that we have on offer to help you guys get the best out of your design. So I'm going to start off looking at introduction, just a little bit of who we are for those of you not as familiar with us. And then we'll get a sort of overview of some of the solutions that we have in Ansys for the sort of different levels of the design optimization that you want to do. And then we'll take a bit of a dive into the PIDO philosophy and how we can kind of fit into that and help you guys achieve those kind of targets and goals. And then we'll finish off with some case study examples, particularly focusing on OptiSlang, and then we'll take some questions at the end. So who we are Qfunsoft. We are local representatives for Ansys in Southern Africa. We've been around for more than 25 years now, with our head office in Pretoria and the local office in Stellenbosch, where I'm based. As I said, we specifically the resellers for Ansys, as well as CF Turbo. We offer all the training and technical support for these products. In addition to that, we also can do some design and simulation consulting work using these products for maybe those clients who don't necessarily have access to any particular product. And then obviously we try and help them where we can and do the simulation work for them. And then also just to highlight that, we talk about Southern Africa as in more than just South Africa where we're based, but right up into the African continent as well. Okay, so that's enough about us. Let's talk a bit more about Ansys. I'm not going to go too much into the background as to who Ansys is. I'm sure many of you, the fact that you're joining this type of presentation, you know who Ansys is, and most likely a user as well. But just obviously stating that Ansys sees themselves as the simulation leader around the world, because that's all they do. They focus on simulation work and simulation products. And more specifically, how do we integrate those products together to give you guys the best experience and the most efficient workflow that we can. So kind of thinking a little bit more about the bigger process, often we tend to, as users, we tend to get stuck in this sort of one area where we're just simulating our particular product. But that is often just part of a much bigger workflow system. We need to connect our simulations of certain components. We need to consider maybe different materials, what materials are available to us, what are we allowed to use, and those kind of considerations. Also, how do we then integrate our component that we're busy designing into a much larger system? Okay, so we talk about things like model-based systems engineering, and it's about designing our component as part of a bigger system. So essentially simulating the whole system. Those aren't necessarily all Ansys simulations. Those can be brought in from other packages as well. And then it's also about linking that as part of a much bigger design management process. Okay, so we've got our SPDM, our simulation process data management system. How do we share our simulation knowledge and findings with the rest of the team? And then obviously as they make changes, how do we receive those? So, there's a much bigger system at work here. But so just kind of keep that in the back of your minds. But for today, we're going to focus mostly on the optimization side of what Ansys can offer. All right, so when we talk about optimization, what exactly do we want to do and how can we achieve an optimal design? So starting off, most people just think of a single design point that they operate at, and they want to find the best design at that particular operating point. But sometimes we need to kind of, well, how do we understand that design point a little bit better? And so that's when we can look at something like sensitivity analysis. So this is where we try and identify what are the most important parameters in our particular design. So we look at certain variables, certain parameters, and we can kind of see how they are linked together. Are they tightly linked or they're very loosely linked? Which parameters have the most effect on the design that we have? Okay, so you could do that either with one design or with many, but sometimes we need to say, what if we change the design? How does that affect our goals, our target requirements? And so we need to then run a much larger study of multiple design points. So we can get some help in this using a design of experiments analysis. So this helps us identify which are sort of or how can we sort of minimize our set of parameters that going into the model, so that we don't have to run hundreds and hundreds of different combinations of design points. Okay, so this just helps us to minimize that field of inputs so we can get to our answers more effectively. Then from there, we can take all of those many simulations that we run, and we can put them together into a response surface. So we build some sort of mathematical model of how do we piece together all these individual simulations and try and get a general trend of how our design behaves. So we can start seeing, are these points that we've selected, are they the most optimum design, or are they sort of still far away from a potential high or sort of optimum point that we can operate at? Then once we kind of get a sense of what is the design space we're working in, we can look at optimization. So either using the response surface from before, or just with other sort of targets or inputs in mind, we can then go about trying to find what is our combination of design parameters that will give us our most optimum design based on our target design goals. Okay, and then lastly, we can look at something called the Six Sigma analysis, or Six Sigma is part of something we call robust design. And this is about understanding how robust our design is, how likely is it that we will actually operate at this design point. It's all very well we've optimized our design, but if it's an unachievable design, then it's also not very good to us. Okay, and obviously as we move along here, we find that we get great or much better understanding of our design and where we're operating, and obviously that leads to more return on investment. So as much as it's a lot of extra work, we do get a lot more value from this type of analysis. So just about understanding what needs to go into to achieve these goals. Okay, and then within the sort of the Ansys space, most of our products do have a basic parametric analysis tool within them, where we can set up our design or our design space of all of our different points that we want to consider. So particularly with products like Discovery, even the electronics products have something called Optimetrics that can manage this process where we've got multiple design points that we need to analyze, so that we don't have to go and set up like 100 different designs. We do it once and just change a few parameters from there. So obviously that's kind of the most basic type of analysis that we can do. So it's a very manual process, but it might be a good start for a lot of people. Then some of our products have sort of a bunch of tools that we can think of, analytic derivatives. So this is where it actually looks at our field values that we've calculated through our simulation, and it allows us to actually change and adapt our model based on that. So something like H versus S, we can actually compute the derivatives of the SYZ parameters, and then we can actually make some sort of instant updates to our design parameters to just tweak those values to a better setting, or something like the adjoint solver in Fluent, which actually can adapt and change your mesh based on your field values and certain targets that you set for, like a pressure drop or something like that. We actually hope to do another short presentation on the adjoint solver for Fluent in the next few weeks, so just keep an ear out for that. But either way, with all these analyses, they are fairly manual, and they're not always optimal, both from the sort of time that you have to put into it, as well as they might not also be the most optimal design. So we typically think of these types of analysis as more just exploring the design space, so kind of seeing what's out there and seeing what some of the options are. But to be more rigorous and to do a more formal optimization analysis, we do need to use proper tools for this. So these are, there's a different few analyses that are available. So, for example, an optimization study or a sensitivity study. Obviously, optimization is trying to minimize some sort of cost function to actually determine whether a design is meets our target criteria better than a different design. Or we can look at a sensitivity analysis, which we've seen before in the previous slide. It's like how sensitive is this design to certain input parameters. So these are generally quite sort of easy to do. So even optometrics within the electronics products can do all of these types of analyses. But when we want to get to a more rigorous analysis, then we do need to move towards a product called Design Explorer. Okay, so this is kind of the full hog in terms of what analyses or optimization tools it has. So it can do the response surface analysis. It can do a Six Sigma robust analysis. With Design Explorer, we can even build ROMs or reduced order models for use in maybe a digital twin, something like that. And because they're essentially a characterization of our design operating in many different design modes. Okay, so if we kind of, and I just mentioned Design Explorer here because historically it's been the application that we've kind of gone to within the Ansys family to do design optimization, because it can do all of these detailed analyses. It's got all these different algorithms available to it, and it's the idea is that it can link to all the different Ansys products. So that's kind of where we've gone traditionally to find the optimal design. Also, I make note because it's something that's available to everyone who works within the workbench environment. So either working in there with your typical mechanical products like Fluent or Mechanical, or if you bring your electronics products in there, you can link to Design Explorer to optimize your design. So it's quite a good starting point for a lot of people to get going with your analysis. Okay, and we can use that to get our optimal design. But another point I want to make is that a robust design is much more than just a simple optimization task. There's a lot more than just looking at a bunch of different designs. Okay, and that's kind of what kind of leads us into the rest of the presentation that we're going to see today. Okay, so going back now to that big picture organogram slide I showed earlier, we need to think about optimization as more than just finding the best component. We need to think about it in terms of the whole process of finding the best product and how it affects the company's design workflow as well. So We often find, in sort of product development today, there's three main challenges. We find that to get the best product, we have to put in a lot of manual work, and it's a lot of iterative process back and forth, and that can lead to quite a slow time to market. To kind of overcome this, we need to somehow find a way to increase efficiency, try and automate things, and get results out faster. We find that also we have lots of requirements that we need to meet, and how do we juggle between all these different, often conflicting requirements? And so, we need to find a way that we can identify the most important parameters to find the best trade-off and improve the product performance. And then, very importantly, we need to consider that the products are either robust from a structural point, but also can we actually manage to build these, or maybe the tolerances are too high or too costly to achieve the goal that we're trying to achieve. So we need to identify areas of cost savings so we can quantify and eliminate any risk in our design analysis. And this is where this sort of PEDO philosophy comes in, this process integration and design optimization. That's what it stands for. So on the left there, we need to consider how do we integrate this optimization into our process? How do we connect the different tools together to get sort of a design that works across the board, not just in one specific package or physics analysis? How do we automate this kind of process to make it faster and more reliable? And how do we obviously make this a much easier process as well? Then on the right, design optimization, that's the actual hard work of optimizing the design. So how can we achieve that goal, but hopefully reducing some complexity, in terms of the work to get there, and maybe even the design itself. And then how do we verify that this design is actually a design that we can meet and actually manufacture and does the job reliably every time? And obviously this is, with these goals of shortening the time to market and improving product performance and eliminating risk. So within this kind of workflow, there's a couple of different ways we can arrange this, depending, what works in terms of your company and what your end goals are. So obviously we need to find a way to integrate these workflows, hopefully try and automate them, speed them up. But then it's also how do we get that information to our end users? Maybe we need to publish them in some sort of web platform where they can access this information remotely, or is it just about publishing the information locally to our colleagues in the office? Okay, and then how do we link that with a parametric analysis as well to optimize our design? All right, so do we bring the parametric or the optimization analysis towards the end of our workflow, or do we somehow try and work it into the process? So obviously we want to automate, but do we automate and then optimize and only then release our results? But maybe a more optimal workflow would be to actually try and parameterize and optimize our design up front, so that we can then sort of knock out all the designs that we're not interested in, focus on the areas that are important to us, and only then do we now try and sort of automate things and then publish that information to our other users or clients. Okay, and this is however way you slice it, we feel that the whole optimization process, we need a really good solid tool to work in the space to allow us to provide an optimum design that's robust and also hopefully well automated to make life easier. And this brings us to sort of the main focus for today, is looking at a product we call Optimisation. Okay, so this is a platform that we have to build up these workflows for parametric analysis, The idea is that it's super flexible. It can be coupled to multiple different solvers, not just Ansys solvers, but also third-party products as well. Something like MATLAB, Abacus, maybe other CAD packages as well. They can also be integrated into this whole workflow. Okay, so the idea is we make it universal and easy to use by pulling in all these other different products. So how do we go about doing this or integrating OptiSlang into our workflow? So one of the easier ways to do it is to work from the Workbench plugin. So this is where we are working in the Ansys Workbench environment, which I'm sure many of you are familiar with, creating different design workflows, linking different physics packages together. We can now build our OptiSlang analysis off this design. Okay, so once you've just set up your initial design, in this case, it's static structural analysis. Once we've defined a whole bunch of input and output parameters, you will see this parameter set block here that will be available in Workbench. And then we can link all of our different OptiSlang analysis blocks to that. So doing a sensitivity study, optimization study, whichever combination we feel we need to do, that becomes available there. All right. So the idea is to kind of make it easy to use, that you can work in whichever interface you feel happy with. So it's not just working from Workbench. We can also, certain of our products actually have OptiSlang integrated into the user interface. So, for example, Fluent or electronics products through Optometrics, you can sort of, there's a direct link to OptiSlang so that you can work in whichever environment you're most comfortable in to set up your analysis. So, for example, here, even discovery, this is definitely a place where we're going to be doing a lot of looking at different designs, trying to figure out where our initial design space is coming from. So this is certainly, there's actually a whole tab here dedicated to this. So we can either export our data and we can open up later in OptiSlang, or we can actually load OptiSlang directly, and a discovery item will sort of connecting block will actually be created into OptiSlang, and then we can work from it there and integrate it into a more detailed analysis. Okay, and then obviously we can work within the OptiSlang GUI environment as well. So the idea is that it's sort of a blank slate. It's very, I guess, similar to Workbench, in that we can drag and drop in different modules depending on the type of analysis we're doing. And so it allows it to be quite flexible and easy to use to sort of customize whichever type of analysis that you're trying to do. So, for example, if we want to bring in our Workbench model here, maybe a finite element analysis, we can then have maybe a MATLAB script to either optimize the design or maybe measure something from the design that we've created. And we have maybe a cost function within Excel. So here we've built up our model piece by piece, and created our own custom analysis. Another nice example here is bringing in Granter for materials analysis. So we have our materials library feeding discovery, and then we actually have both a cost and a carbon calculator from that, so we can actually then quantify how well our design is from a cost point of view, but also maybe from an environmental friendliness point of view. Maybe changing materials might affect that, but still give us the performance that we require from the component. So we can get quite creative. In some industries, in some companies, for example, here Bosch, they've actually gone and linked multiple parts of their whole design process, not just the design side, but also manufacturing, the sourcing of components and the supply, where do they come from, and they've kind of integrated that into a more complex model so that they can look at the entire design chain and try and find out what is, try and minimize any bottlenecks in that whole process. Okay, so how does OptiSlang work, and kind of what is its functioning? Because we'll see some of this terminology over a few more slides down the line. So basically, OptiSlang works on something we call a meta model. So this is meta model is essentially just a model of a model. It is a meta modeling is the process of generating these kind of models. So the idea is that OptiSlang will build these meta models from our analysis, and the idea is to give very quick feedback. So obviously doing a full 3D simulation is quite time consuming, but if we can work on a much higher level model, simpler model, we can get much better feedback much more quickly, and then we can analyze a lot more different designs. Okay. So typically, when we work with hundreds of different sort of parametric designs, maybe, we need to kind of say, well, what happens in between the design space? Maybe there's an optimum that we don't really know exists. But obviously, we need to try and automate this. And this is where the meta modeling approach comes in and says, okay, how can we just mathematically describe our design space? But then also, how do we link all of our different criteria together? And so it uses these meta models and runs through thousands and thousands of different sort of options. Don't think we talk about simulations, but they're not full 3D simulations. They're these meta model simulations. And by running through so many, it can find us the optimum design space. Okay, and then we can also kind of link this with some sort of machine learning technique that can then sort of piece together all these different design points that it's looked at, and find a way to get the most optimum answer, or the answer that meets all of our design criteria. So the idea with using these sort of machine learning algorithms is that we use them to guide the simulation, to find the most optimum design and try and get rid of any sort of random results or criteria or results that don't meet our design criteria. And this way we can then improve efficiency and also then sort of get to the important criteria of what actually drives our design, and then we can understand our design much more deeply. So finding the best meta model approach can actually take a lot of time. There's a few different methods out there. So OptiSlang uses something called the auto MOP model. Or sorry, I should actually talk about the MOP. We talk about a meta model of optimal prognosis, the MOP. So this is just the name of the meta model that we use within OptiSlang. So it's based on sort of essentially an automatic machine learning algorithm that finds the best approach to actually get us the result. So it takes a look at the design, the data set that we have, and looks at certain criteria, and that way it can find the best meta model that we need for our particular analysis. And we call that the adaptive meta model approach, or the AMOP, as you might see in some of the literature. Okay, so yeah, and then the idea behind this is that what the MOP does is it sort of essentially runs through your design set, finds out which values have the most influence, and then it can actually then sort of focus in on those areas and kind of populate more design points in those particular areas, giving us better resolution and therefore also better confidence in our results. And then all of this kind of happens quite quickly. I mean, in the latest version of OptiSlang, we call this a one-click optimizer. So the idea is that it takes a lot of the work and decision-making from the user and looks at the results to determine the best algorithm to use. And so you can get going much more quickly, but still have the confidence that you're going to get a good answer. Okay, so we find that, using this kind of AI machine learning techniques in tandem with 3D simulation and also these other CAE tools, we find that we can then significantly enhance the design exploration sort of phase and the optimization phase of our design, and getting to a much more sort of automated workflow and which will ultimately make things far more efficient. Okay, so I've just got a little video here to just run through the optimization process. So this we'll look at I guess the process integration part of OptiSlang and how we can go about setting up a model. So you can see, okay, it's a little bit sped up, but the idea is that we have we can build our model from multiple different products. In this case, we're bringing in a LS-DYNA model, and we're actually using the input script from that LS-DYNA model to set up our analysis. So bringing our input parameters are actually copied from the input script, and then we can also then define our we call it the responses. Those are basically our output parameters. So once we've defined our range, or not only what the input and output parameters are, but also what range they work in, we can then define our objective function. So this is what we are going to be targeting to optimize. And then we also define our constraint equations, which basically define the limits of within our design space. Okay, and you can see here, we've created our basic little workflow with our LS-DYNA model. And then obviously we can also drag and drop additional components into it as well. Okay, so we've got our LS-DYNA solver there with an Excel cost function as well to calculate additional criteria. And then at the end, we can also then select the algorithm that we want to use to solve. In this case here, we've got our AMOP model that we've created, and we're bringing in our optimization wizard to then take that meta model, and then we're going to optimize based on that. Okay, in this case, using an evolutionary algorithm. Okay, so you can see here, obviously it's a little sped up, but the process is relatively quick and easy to sort of build your analysis from all the different individual pieces that you need. Okay, then looking at now more the design optimization. So what do we do with this model once we have it? So no play. Okay, so from our model, it generates a output, particularly looking at our coefficient of prognosis. This is basically linking all the design variables together and saying which variables are the most impactful on our design, and how which ones are the most connected, and in what sort of side of the range are we looking for the best design. And then from this, we can then go and generate different types of plots. So we can look at maybe all the different variations and see where we are in terms of our optimal design. so we can get a much better understanding of the design space that we operate in. Okay, then just having a look now, focusing on some of the more specific features within OptiSlang and kind of what sets it apart from, for example, a Design Explorer or something like that. So obviously the basis of any task that we're going to do within OptiSlang is based on a sensitivity study. The idea is that we want to understand and characterize all the different variables or parameters that go into our model and see which ones are the most important, because obviously we don't want to optimize the ones that have very little relevance to our design. So we start off building our metal model and then doing a sensitivity analysis on that. And often when we think of sensitivity, we'd look at just single parameters and see how that single parameter varies. But obviously, it's not always obvious that that value is going to give us the resulting data if we just look at that single value. Maybe we need to look at something a little bit bigger. And so we can look at maybe a whole signal input, so an input that varies, and have a look at maybe something within that signal actually drives our optimum design. Or looking in terms of physical space, we can also look at how does a variable value vary over a certain area, maybe over a 2D surface area. How does the parameter field vary? And maybe we need to find an optimum somewhere within there. So we actually need to affect the entire surface, not just one particular point or one scalar value. And then we can also do this in 3D as well. So it's about what is the optimum design over a whole 3D component, and not just finding the average value, peak value, something like that. Yeah, so that is sort of quite a powerful extension over just a simple sensitivity model. We can then need to consider the robustness of our design and also the quality of it. How can we actually achieve the results or the optimum design that we have? Because obviously it's not very useful if our optimum design is not achievable, or maybe we need such high tolerance that it's just not practical or cost effective to achieve. So it's about how can we now measure our design based on something more than just the optimum, something a bit more of a quality metric. So quite a handy feature is looking at the actual manufacturable quality or statistics of our components. So in this case, we're considering a little turbine wheel here. We've actually manufactured a few different components, and then we go ahead and measure them, and we try and basically quantify the manufacturing tolerances. How well did our manufacturing actually achieve our target shape, and also what is the variation and where does it vary? So in this case here, we can actually generate a map of where's the areas of the highest deviation from our sort of design shape, and so we can know, okay, well, those areas are probably going to affect the performance because we have the least control over those specific areas. So we can then take this shape, so we generate that 3D shape from our different scans, and we can then actually put that into a simulation and kind of see, well, okay, based on the variation that we expect in the design, what is the result variation that we're going to get? In case of this turbine wheel, maybe there's what is the real pressure drop that we're going to experience across here? How is it going to vary from what is the range that it's going to vary, and how bad is that compared to what we designed? Yeah, so it'll actually take the geometry and morph it into the different range of those sort of extremes of what we've measured. Sort of a slight variation on this project done by Siemens. So this is actually looking at the turbine casing for gas turbine. And so what they also did was measure the geometry and essentially created a sort of measure of all the different sort of thicknesses and how they vary across the design. And then we can go and look at, in this case, what is the range of stresses that we expect based on these imperfections in the design, or the variations in the shape that we can expect. So that's quite of a handy tool to understand, how can we actually, can we actually meet our design targets, and and can we trust the quality of our design? Another interesting use case is looking at not only just the performance of the object, but the cost performance as well. So in this case, we have a particular design that we needed to sort of, obviously cost was a big aspect of the design apart from its actual structural performance. So considering things like material cost and manufacturing costs, we found a design that still meets our criteria of deformation and obviously sort of material stress and so on. But we could actually then reduce our manufacturing costs quite significantly. All right, so that was, that it's not just about the physical structure itself, but can we look at time and cost as a metric for optimization as well? Okay, so now I want to go on to a couple of different use cases here, where we can see how OptiSlang has been used in some different scenarios. So first example here is looking at a electronic PCB. So we have a PCB with a few different chips on them, as well as heat sinks. Obviously, during operation, we expect this PCB to get quite hot. So how do we now optimize our airflow, optimize our heatsink components to make sure that we now get a design that is going to be reliable and safe to use, and it's not going to overheat. Okay, so this can be done either through Workbench. So we have our geometry module over there, feeds into our IcePack thermal analysis, and we can actually look at a static structural analysis, in this case for deformation of the components due to the thermal distortion. And then down here, we can see we have our OptiSlang set up there. So this can either be done through Workbench, or you can actually build in an IcePack node here within the OptiSlang interface. But now specifically looking at the results. So the goal of the analysis was to minimize the stress and deformation in the components. So that's the objectives from the FEA side. On the CFD side, we also have our own objectives in terms of minimizing pressure loss and thermal resistance. So obviously, we've got two different physics that we're considering, and both have their own objectives that we want to try and meet. Maybe this is two different design teams that are also trying to meet their targets. So how do we now sort of keep down the mass and the temperature of the heat sources and make sure this all works as expected? In this case, we basically playing with the heatsink parameters, so the number of fins, the thickness of the fins, and also the flow rate. And in this case, we can even vary the position of where we position the fans in the housing. Okay, so there's a lot of different parameters that we can change within here. So again, how do we find the best layout and what actually is going to have any effect on our goals? So here we've conducted a sensitivity analysis. In this case, over 100 designs. Obviously, not all of them simulated. Some of them would be filled in with the meta model. And we can now have a look and try and quantify which of the different parameters have the most effect here. So if we look at the sensitivity of, this table here, this is our sort of coefficient of performance table that quantifies how the different parameters work relative to each other. On the bottom here, we can see the different parameters that we've tested. And then on the left here, we can see which are the most important, or which of our targets or goals have been affected. So from this matrix, we can see that, out of all the 12 parameters that we could change in the design, only really sort of 10 of them have any real influence. And in this case, if we look closer, even a few of them have actually very little influence as well. If we look at the numbers, and obviously these blanks here indicate very little, or essentially zero influence. Okay. So in this case here, we can see that, we have quite and also if we look, at the response surface here on the right, we can also see that, we get quite a good fit. We don't have too many outliers in our design, so we can then therefore have a little more confidence in our results. Okay, so if we start actually now looking at the different designs, so we ran, in this case, up to 6,000 designs using our meta model, and you can see that we kind of have this sort of clustering here on the bottom left. All the gray dots indicate constraints that have been violated. So these are designs that we probably cannot achieve for whatever reason. And so we kind of want to focus on this area of the black dots, and particularly on which ones are going to be the best performers within that grouping. Okay. So there's a number of different metrics that we can use here to analyze it. I have another little design here little video that will just quickly run through setting up the model, as well as having a look at the design or analyzing the criteria. So what we see now is a typical setup within Workbench, a typical parametric model with all of our different design inputs that we've, or parameters that we've defined in the different components. So you can see there that we have a geometry block, our icepack model, as well as our static structural. Now we're dragging in a sensitivity analysis into Workbench, and that links to our parameter set. Okay, and from that parameter set, it automatically picks up on all of our different inputs and outputs that have been defined, and we can specify the different ranges available to them. Okay, so on the top left here, you can see we have a list of parameters and list of objectives that we need to look at. And now we're defining the type of sampling method that we're using to set up our meta model. Okay, Optimisation uses that kind of traffic light system to try and guide you as to which would be the most appropriate algorithm to use for this particular case. Okay, so now that we've finished with that setup, it's just busy updating our meta model to use this. And now we are bringing in an optimization onto our sensitivity study. So we've done the sensitivity study. Now we're going to optimize it and try and find and use the object or the parameters that have been highlighted by the sensitivity study. And we're now going to use them to optimize our design. Okay, so we're busy now adding certain criteria. So these are our objective criteria here. So these are what it's actually going to be using as a target or a goal for our design. And then we move into the next stage, and you can see here it's indicating that we want to use an evolutionary algorithm for our setup. Okay, then we can update that design, and it will fairly quickly generate that optimization results for us. Okay, and so now opens up our IcePack, our IcePack, our OptiSlang interface. So you can see here that we are now, in this case, working from the OptiSlang side. We're not actually working from Workbench. So we're just defining our project within OptiSlang so that we can then do some post-processing. So we're telling it which are our input parameters, which are the responses that we want to see in our output data. And then we can run our analysis. Okay, so you can see it's created our IcePack mechanical workflow there, and we can add to that if we need to. So we can build and customize our design a little bit further. Okay, so now we're just seeing that in the different work node there, the IcePack mechanical node, we can add different inputs or outputs and connect the different outputs or different blocks together to build our custom model. Yeah, so we're just dragging in Excel there to help do some calculations for us. And also a MATLAB script. So obviously, I should note that you do need these packages installed on your machine if you want to use them. We don't provide MATLAB, for example, so you will need those packages to be able to use them. So now that we've run our analysis, we can have a look at the results. So you can see our COP metrics on the right there, as well as our individual sort of COPs at the bottom. If we double click on a certain combination within our field of view, it will then also highlight the specific combination in the little graph there and in our sort of graph plot over here. What we've just done now is add a visualization of our stress results. So this is our the mechanical stresses in our 3D model. So if we now go and select different design points, so that's what we're doing here, selecting different design points, you can see that the actual the number of fins and the thickness of the fins and all of that will update to our current selection. Okay, so these are our values that will exist that we can then look at the individual results. So you can see now once they're rotated around, we've got a much thicker, denser distribution of heat-sink fins, and we can actually see the deformation of those fins together. And you can see some of them in the middle there might actually be touching during their deformation. Okay, I just want to do one. I know we're running a bit tight on time. I just want to maybe do one more example, just so they can get a feel for some other uses for OptiSlang. So now we're looking at, in this case, a turbofan for a civil aviation jet. So here we are taking our input parameters from the geometry. So this could be blade modeler or something like that. And then we link that into a much more complicated model where we bring in sort of CFX, TurboGrid, do structural analysis, all of that. And then we do our OptiSlang analyses on top of that. Okay, so obviously in this case, we are looking to optimize our polytropic efficiency through the turbine. And we can change, in this case, 25 different parameters that will affect the shape of the blade. All right, so in this analysis, we obviously need to go do a sensitivity analysis, see what are which values are going to have the most bearing on our analysis, because we put in quite a few input parameters. So from the analysis there, we can kind of step by step go through everything. And in this case, we can see that our meta model for display has a reasonably good sort of a relationship there of 66%. And we find that 8 input parameters have the most influence on this response. Okay, so we can then now focus our analysis particularly around those values. But maybe in this case here, 66% so p-value might not necessarily be the best that we are looking for. We feel we can do better. So how can we then go about trying to improve our accuracy or sort of reliability or fit of our different data points? So one way to do this is we can actually go, before we take the step, we can actually go and deactivate some of the outliers. So we can actually go and from this plot and actually remove them from the analysis. Maybe these guys at the top are just so far out of the way that we just don't want to consider them as possible input parameters. So we're kind of narrowing our scope of our model. Or we can then go back to the actual constraints that we put on the model. Maybe we split up some of our constraints into a few smaller ones, so we're not trying to change too much in one go. We can or split it up in different regions of our model. Maybe that will help. And then we can also maybe go and remesh the model as well. Maybe the model lacked some refinement or had some poor quality cells that were influencing our results, and that would then sort of feed into the mess. All right, so I think I'll leave it there. There's a few more case studies if anyone's interested, but I think in terms of interest of time, I don't want to keep you guys for much longer. So yeah, just thank you guys for your time. And if you have any questions, I'll be online for a little bit longer, and we can always, or we can catch up at another stage if we want to take it offline.